Hello everyone, welcome to software testing. My name is Peter Atiyah, and today I will be talking about detecting anomalies, causes and effect. So what is an abnormal? Abnormal in computer science software is the contrary of the normal or expected behavior of a program. So why not use assertions like presented last time in all the program and detect the wrong behavior? Well, assertions take time to write, especially in otherwise unspecified or undocumented code, and assertions over temporal properties don't call close unless you have called open or control flow. So if you have taken this branch, you cannot take this other branch, and these are difficult to specify. And for practical purposes, assertions cannot cover all properties of the entire state of all times, because this would imply a specification as complex as the original program, and just as likely to contain defects. So there will be always gaps between assertions that must be explored. So the solution to this is having assertions comparing against normal behavior, and so detect behavior that is abnormal. So we're not detecting only the anomalies. Why only abnormal and not wrong behavior? Abnormal behavior is a good indicator of defects, so it is better to detect anomalies than further focus on their cause. And for the abnormal characteristics, the code coverage. There is code coverage, call sequences, and variable values. For the code coverage, code that is executed in abnormal failing runs, but not in normal passing runs. For the call sequences, sequences of function, calls that occur only in abnormal failing runs. And for the variable values, variables that take certain abnormal values in failing runs only. So detecting the normal behavior can be done in many ways, and one of them is the induction technique, which is inferring an abstraction from multiple concrete events. Compare the coverage. One of the simplest methods for detecting anomalies operates per the following logic. Every failure that is caused by an infection, which again is caused by a defect. 2. The defect must be executed in order to start the infection. 3. Code that is executed only in failing runs is more likely to contain the defect than code that is always executed. Coverage tools are used to detect failure. So, instrument code such that the execution keeps track of all lines being executed. Such coverage tools are typically used for assessing the quality of a test suite. A test suite should execute each statement at least once, because otherwise a defect may not be executed. And the code used such coverage tools to compare the coverage of a passing and the failing run. And this code snippet shows how to do this. So you can see that there is conditions for each one. So if y is smaller than z, or if x is bigger than z, and for each checking there is a different return. The next thing is Tranutula, the code visualizer, tool for visualizing coverage anomalies. In the Tarantula, each non-blank character of the code is shown as a pixel. Each line is assigned as a color, hue, and a brightness, indicating the anomaly level. As you can see in the picture on the right, this is just a picture of the tool. So for the color, the redder a statement, the higher the percentage of failing test cases in the test cases that executed this statement. In the last example, line 8, you would get the highest amount of red, as 50% of the test cases that executed this statement failed. And in line 5, 6, and 9 through 11, you would appear as green, as they were only executed in passing tests. And just take a look at the code and you can see the difference. And for the brightness, the brighter a statement, the higher the percentage of test cases executing the statement in all test cases. And this tool user would be searching for then is bright red line statement that are executed in failing test cases only. And in the best of all worlds, only a few of those lines would show up, limiting the number of lines to be examined. Facts about anomalies. For some defects, the percentage of abnormal code was as low as 3%. That is, starting the search at most abnormal category. The programmer would find the defect after looking at 3% only of the code. The most abnormal category, the 20% reddest, contains at most 20% of the code. That is, comparing coverage actually yields small significant differences. And 18 out of 20 defects were correctly classified in the most abnormal category. That is, the one containing 20% at most of the code. And abnormal statements allow programmers to ignore 80% of the code or more in the previous case study, which we had in the code and everything. And in the case study in 2015, applied this technique on a test suite based on the Java Nano XML parser. They found that sequences of calls always predicted defects better than simply comparing coverage. Overall, the technique pinpointed the defective class in 36% of all test runs, with the same low cost as capturing and comparing coverage. Dynamic invariance. Another approach for leveraging multiple runs is to generate likely specifications that hold for all runs, and to see whether these can be turned into general assertions which can then be used to detect anomalies. Also, a simple yet high effective approach has been implemented in the DICON tool by Ernest. The main idea behind DICON is to discover invariants that hold for all observed runs. These invariants come in the form of pre and post conditions. They can be converted into assertions to check for abnormal behavior. For the code on top right, processing 100 randomly generated arrays with a length of from 7 to 13 and elements from -100 to a +100. Running DICON on these runs yield to two invariants. The first one is the picture on the right under the code, which is inferred precondition for execute 1511. And the second is the post condition, and you can see the difference between the arrays and the return statements in each of them. How does the DICON detect these invariants? So the general process goes as follows. The program to be observed is instrumented at runtime such that all values of all variables at all entries and exits of all functions are logged to a trace file. For C and Java programs, DICON uses binary instrumentation techniques. 2. When executing the program under a test suite, the instrumented code generates a trace file. And then the DICON processes this trace file, and DICON maintains a library of invariant patterns over variables and constants. Each of these patterns can be instantiated with different variables and constants. While detecting invariants, DICON makes some optimization to make the remaining invariants as relevant as possible. In particular, if some invariant A implies an invariant B, then B need not to be reported. After DICON has fully processed the trace file, the invariants that remain are those that held for all execution points. Then DICON ranks the invariants by the number of times they actually occurred. An invariant detected 100 times is less likely to be a random effect than an invariant detected 3 times. DICON reports the relevant and ranked invariants to the user, and the invariants can be fed into another tool to further processing and to detect the bugs and the anomalies. Using invariants. Method specifications come as pre and post conditions as discussed before, and they can apply to the primitive data types such as integers, and they compare at most three variables with constants and other variables, as in the picture on the right. And composite data such as sequences, arrays, lists, for instance, a subsequence B where X belongs to A and A is sorted, and that is in the code snippet below the picture in string content string.length, and this is how it applies to it. And for the object invariants such as the following, that also can apply to primitive data and composite data. For the matching invariants, for each variable or tuple of variables, DICON maintains a set of potential invariants, initially consisting of all invariants at each execution point under consideration. For each value recorded in the trace, DICON checks each invariant in the whether it still holds. If it does not, DICON removes it from the set. Value ranges. A question not yet answered is whether dynamic invariants can be directly used for anomaly detection without first selecting those that are useful as general specifications. Just like DICON and deduce instruments, the code of the program is in question. In contrast to DICON, deduce works on the fly, and that means invariants are computed while the program is executed. So for each instrumented place in the program, deduce stores three items. The coverage is the deduce counts the number of times the place was executed. The values, for each accessed variable, deduce stores the found value of the variable read or written. This value is converted to an integer if necessary, and then stored as a pair of v and m, and we'll have the explanation in the picture below. And then the difference, for each variable, deduce additionally stores the difference between the previous value and the new value. These are stored as pair of v and m as described previously. And this is just a picture that shows a simple run for the deduce and there are different results in it. For the sampled values, in addition to simple coverage, there are other aspects to collect from actual runs. Exceptional behavior of functions as indicated by exceptions being raised or unusual values being returned. If such events frequently occurred together with failures, we might have important anomalies that point us to the defect. Liblet at AL attempted to use remote sampling to isolate the defect in release 1.2 of the CEN4072 encryption tool. So for them to gather data from actual runs, the company generated 2,990 random runs from random present or absent files, and they were randomized command line flags and randomized user responses, including occasional end of file conditions. These runs were classified into failing or crashing and parsing runs. So the results came out to be that in the 2,990 test runs, only 2 out of 1,170 counters satisfy the following conditions. The traverse of the file exists and the traverse of X read line, and such result is an anomaly because it occurs only in failing runs and it is not a defect, so because both return values are perfectly legal. So anomalies and causes. An anomaly is not a defect and it is not a failure cause, yet an anomaly can be a good starting point for reasoning. Does an anomaly indicate an infection? If so, we can trace the dependencies back to the origins. Could the anomaly cause a failure? If so, we must understand the effects of the anomaly, for instance, by following the forward dependencies through the program. So could the anomaly be a side effect of a defect? If so, we must trace back the anomaly to the common origin of failure and anomaly. So all the time we have to go deep into the anomaly to detect the cause of the problem. For the tools, deduce. This is a Java debugger, and deduce is an anomaly detection system that helps in automated debug of Java programs. It instruments a program's bytecode and monitors values and types of objects in one or more executions of the program. It attempts to detect anomalies such as new values for a variable at a program point. Such anomalies are ranked statistically on the basis of how large the deviation is from the past values seen at this point and how often it was executed. The second tool is the daikon. And for the daikon, it uses invariants. So the daikon is an implementation of dynamic detection of likely invariants. That is, the daikon invariant detector reports likely program invariants, and an invariant is a property that holds at a certain point or points in the program. These are often seen in assert statements, documentation, and formal specifications. Locating errors versus locating causes. Locating errors. An error causes a failure, and the error is often difficult to establish. So you cannot always recreate the same error all the time. Some errors are hard to actually establish again. So an error is a design flaw or a deviation from a desired or intended state, and an error will yield a failure without the conditions that trigger it. And an error refers to difference between an actual output and an expected output. So the user will put in a certain input and he's expecting an output, but he receives a different output, and that is the error. Locating causes. A cause is an event preceding another event without which the event in question would not have occurred. So, a defect causes the failure if the failure would not have occurred without the defect. So, once the cause is found, the error is not far away. So, once you found the cause, you probably are on the right track to finding the error and fixing it. Causality. Can we provide causality in software engineering? Well, reasoning alone does not suffice for providing causality. We must show by experiment that if a cause is not present, an effect is not present. As an example, a equals compute value, and compute value is just calling a function, and it should get a return. And now we're just printing the a value to the user. So this piece of code invokes the compute function and assigns the result to the variable a and prints the value of a on the console. When executed, it prints a equals 0 on the console, although a is not supposed to be 0. So what is the cause of a0? Now we know that we have an error in our hand. So after deducing the problem from the program code, the invocation of compute value is a possible reason behind the error. And after investigation, the assignment function, we find that it should not return 0. So that being said means that compute value returns the wrong return value, so we need to investigate it more, and we need to dig more into compute value to find the cause of the error. So detecting the causality is based on building different hypotheses and tracing them till the actual cause is detected. Verifying causes. The actual world. The actual world is in which the effect occurs is our real world, with the effect, the failing run, occurring before our eyes. In the alternative world, this is what we need to show that some property causes the failure. To show causality, we must set up an experiment with an alternative world, in which the property does not occur. If in this statement, in an alternative world, the failure does not occur either, we have shown that the property caused the failure. This type of reasoning is called post hoc ergo propter hoc, which means after this, therefore because of this. This means that an anomaly has occurred before the failure, and therefore the anomaly must have caused the failure. As an example for that for this method, consider a program that emits a warning message, say, configuration file not found, and then fails. How do we show that the missing configuration file causes the failure? We set up an alternative world in which a configuration file is present. In other words, we set up an experiment to support or refute our hypothesis about the causality. If and only if in our experiment the failure no longer occurs, have we shown causality. That is, the missing file caused our failure. Causes and differences. So, now we need to narrow down the causes. And for that, we need to go through some steps. The first step of that is find an alternative world in which the effect does not occur. Narrow down the initial differences to an actual cause using scientific method as discussed before in the scientific debugging. If you think that this sounds almost trivial, well, that is absolutely right. The alternate world where the effect does not occur is not this, just what we aim at. Think about an effect caused the failure. For instance, if we have an alternate world in which the defect does not occur, we are already set. Why bother dealing with the differences to the real world if we already know what the alternate world is supposed to be? Well, the alternate world need not to be a world in which the program has been corrected. And the challenge in that is to identify the initial differences, which can then be narrowed down to an actual cause. Isolating causes. Actual world. What is the actual world? The actual world is a world where the defect occurs and where the failing of program happens. So now we need to make an alternate world, and that is where the effect does not occur and as close as possible to the accept of the cause. And now we have the mixed world, which is a common context between two worlds, which includes that the program is executed and necessary conditions for every alternate world. So we have the world that has the problem, and we have an alternate world that is very close to that world, and where the problem does not happen, and we have the common context which is the middle ground between both, and the picture down explains that more. Causes and effects. What are the causes? Causes are the most valuable during debugging, and a cause is an event preceding another event without which the event in question, which is the effect, would not have occurred. And a cause can be seen as difference between the two worlds, the alternate and the actual world, and a world in which the effect occurs and an alternate world in which the effect does not occur. And the effects occur in when the cause occurs, and the effect does not occur when the cause does not occur. And the effect may occur due to multiple non-trivial causes. So the effect requires experimenting to detect the actual cause. Finding actual causes. It turns out that finding a cause is trivial, but the problem is to find the cause among a number of alternatives. So what does that mean? So, to further explain that, we're going to use the previously explained example, which is a compute value assigned to a variable called a and then printing the value of a. We could also say that the printf statement as a whole is a cause for printing a equals 0, because if we remove it, nothing is printed. And we could also say that anomalies, as discussed previously, detecting anomalies, are the cause of failure, because without anomalies, the failure does not occur. We can treat the entire program code as a cause because we can rewrite it from scratch such that it works. So this multitude of causes is unfortunate and confusing. We just have a few or bunch of trivial causes that has nothing to do with the actual problem. So in debugging, and especially in automated debugging, we would like to point out a single failure cause, not a multitude of trivial alternatives. Alteration. The concept's actual cause and closest possible word are applicable to all causes, including the causes required for debugging. So, if we want to find the actual cause for a program failure, we have to search for the closest possible word in which the failure does not occur. For that, we have the input, which is the actual failure cause in a program. Input is minimal difference between the actual input where the failure occurs and the closest possible input where the failure does not occur. The state, which is the actual failure cause in a program state, is a minimal difference between the actual program state and the closest possible state where the failure does not occur. And the code, which is the actual failure cause in a program code, is a minimal difference between the actual code and the closest possible code where the failure does not occur. That's why most of the companies and most of the programmers keep different versions of their software so that they can always go back to the previous version and check the difference between the current version and the previous version, so that way they can detect the error in the code. What is the failure? So all of these failure causes must be verified by two experiments, one in which effect and failure occur and one in which they do not. Once one has verified a cause, one has a valuable information for debugging. Causes are directly related to the failure. What does that mean? As a failure is an effect of the cause, it only occurs when the cause occurs. So neither defects, which is deducing errors, nor anomalies, which is detecting anomalies, are as strongly related to the failure. And failure causes suggest fixes. By removing the failure cause, we can make the failure disappear. This may not necessarily be a correction, but it is at least a good workaround to start from. And both properties make causes excellent starting point during debugging. And as always, finding a bug, but nothing wrong with the code. Thank you so much. My name is Peter Atiyah.